In this video, we're going to look at two different situations when you're driving in your car going around a turn. In the first situation, we're going to be on a banked curve while we go around and make our turn, but there's no friction involved. So here we already have a picture of the car as it goes around the banked turn. Our normal ideas of weight going straight down and then the normal force perpendicular to the plane still hold true in this case. Now we have additional components for our vehicle as we're going through. So first we're going to look in the X plane and the forces that are at play. Because I am moving in a circular manner, I'm changing my direction and I'm accelerating. So here the net force is equal to mass times acceleration. And the net force is this actual component of the normal force. Remember, it has to be something physically moving me, a physical presence there that is moving me in a circular path. So here the net force is caused by Fn normal force times the sine of theta. And mass times my centripetal acceleration is v squared over r. So I have that equation in the x-plane. Now in the y, I'm not accelerating. So here, the net force equals 0. Well, the sum of all the forces is Fn cosine theta minus mg is equal to 0. So I have two equations, and what I want to do is I want to solve on the y side for the normal force. So if I get mg on the other side, normal force cosine theta equals mg, and then I divide both sides by cosine theta, I wind up with the normal force is equal to mass times gravity divided by the cosine of theta. I can just insert this part of the equation over here. So when I combine, I wind up with mg over cosine theta times the sine of theta equals mv squared over r. Now, what happens to the mass of my vehicle? Well, like most things Newton, it divides out. And what is sine over cosine? Well, that turns out to be tangent. So tangent of theta, and I'm just going to take my g and move it down here, is equal to v squared over r times g. And with this equation, gravity is known, so if I either know the angle or the velocity or the radius, I can solve for either one. So that's our first scenario. In our second scenario, I'm on a flat bottom turn. But now I have friction for the vehicle. So if I were to draw a free body diagram and kind of flip the plane, so here's my car, and it's coming out of the page at me for a free body diagram. Gravity would still be down. The normal force is up, and as it's going around the turn, it's the friction force which would keep it moving in a circular pattern. Remember, all of a sudden, if there was ice under your tires, your car would just veer off the road and continue to travel in a straight line or a direction tangent to what was its current path. Now, once again, it's not centripetal force that moves us in a circle. There has to be something physically there. So it's the friction force of the tires and the road that's moving us in a circle for our centripetal acceleration. So if we expand this equation, the friction force is...
May I have your attention, please? All custodians, please report to the 600s. All custodians, please report to the 600s.
is mu times the normal force, and here we have mass times velocity squared divided by my radius. If we expand this a little more, we know that the normal force is mass times gravity times mu is equal to m v squared divided by the radius. What happens to the mass? Once again, boom, it cancels out. So if I'm looking to solve for the maximum velocity, it would always be equal to r times gravity times whatever the coefficient of static friction is. Because once you start hitting kinetic friction, that's when you start to skid out and lose traction with the road. So from there, you can solve for any of the variables that you need. All right, those are our two situations for today.